Good morning. Thank you very much for having me today, and thank you for organizing the conference. It's really been great to talk about all the different ideas, and I hope the result of this will be more research, more investigations, more questions we can try to answer. And thank you also for the previous speakers who have laid the groundwork for my talk, Donald and also James. It makes it easier for me. So I will try to answer the question, how could this possibly work in an elastic solid universe? So first, just briefly about the motivation. Then I'll preempt some criticism that we might be getting from other people, and that's related to the question of wave versus particle. Hasn't it been proven that there are actually particles? What about the Stern-Gerlach experiment? And then I'll talk about the elastic solid model, and I'll try to touch upon several topics, including relativity, electromagnetic waves, spin 1/2, and if there's time, talk about charge as well. So what has been motivating me is just some really basic questions. I just want to know how a magnet works, and nobody could answer the question for me ever. I wanted to know what is spin, and again, nobody could have a good answer, so I figured I have to research this myself. Also, what has been bothering me is there are all these interpretations of quantum mechanics. I mean, why are there like 10 different models of quantum mechanics, right? Like, you don't have these different models about cars. Imagine we had 10 models of how cars work. That would be really weird. We want to investigate how the mechanics works of a car. So that's what I'm trying to do. And I've coined this sort of the neoclassical model, where basically the assumption is that at least some part of the wave function is real, maybe not the whole one, and also that everything has a mechanical basis. So first, let's talk about two topics of quantum mechanics. First one is about photons. Now here, I first want to talk about phonons with an N. So what's a phonon? So you may have heard of this, a particle of heat or quantized sound waves. Sometimes they're also called quasi-particles. These are basically things studied in material science when you want to investigate how heat moves in a transistor or any material, how these heat disperses. And these are just normal vibrational modes in a solid or in a crystal. And if you look closely, it does resemble, it has resemblance to photons, right? If you look at this. Oh, by the way, I have a lot of simulations, and all of them are online. All of them are available to everyone. You can have the source code. You can change it however you like. So what is a phonon? Now, it's basically a quantized vibrational mode of a solid. It could be like a crystal, as an example. Here's some more pictures. It is an emergent collective excitation, and it's described very similarly to a photon. The thing is, here, nobody in their right mind would say, oh my God, this is a particle, right? It's clear there's a vibrational mode. There's nothing mysterious about it. You don't need a parallel universe if you measure it or anything like that. So I've always wondered, well, why should it be different for photons? And the funny thing is, you can even do double-slit experiments with these, like phonons. There are also plasmons, polaritons. These are all quasi-particles. And you can actually film it, right? So you can see the wave interaction. You can see what happens in a double-slit experiment. And there's nothing magical about it. So why should it be so different for photons? Well, here comes the photoelectric effect. Supposedly that was proof that there are particles. And the reason is, in the old times, in the classical view, they thought, if we shine more intensive light onto the metal, the electrons that get emitted should move faster. They also thought that any frequency should work, and that it should take more time for low intensity. But what they observed is something different. What they saw is that when you have more intense light, there were more electrons, but they weren't faster. And also there was this minimum frequency required, which was kind of weird. And they didn't see any delays. Interestingly, Einstein got the Nobel Prize for this, so it's kind of hard to dispute this. But the thing is, you have to look in the historical context. A lot of things weren't known back then. For instance, quantum mechanics has not been developed yet. Schrödinger did not have his wave equation yet. Fermi's golden rule has not been developed yet. This came all later. They didn't know the electron had quantized energy levels. So if you didn't know all this, well, maybe that was a reasonable conclusion, right, back then. But now we know a lot more things. Maybe we should revisit these old experiments and reinterpret them with the knowledge that we have right now. So what is Fermi's golden rule? What it does, it calculates the probability of a transition from one energy level of an electron to another energy level due to a weak perturbation. What's a weak perturbation? That could be like an electromagnetic wave that's coming in. And what you see here on the chart on the left side, it tells you that if the frequency matches exactly to the energy level difference, there's a high probability that the transition will happen. And as you deviate from this, the probability will get lower. But you don't actually need an exact frequency match. It can be just close. It will also work. In addition, so this is actually due to resonance. What is resonance? Resonance is something we observe in many, daily events. Things like there has been this Tacoma Bridge that almost broke because of just a wind that happened to create a harmonic resonance. And this wasn't a storm, okay? This was just a wind. And the point is that when you have even when you have a resonance, it builds up. The wave motion builds up. At some point, you can get it to a breaking point. Similarly, when you sing the tone of a wine glass, if you manage to sing that tone, you can actually break it over time. Yes, go ahead.
Just real quick, you're saying that there's a connection between resonance and Fermi's golden rule?
Yes.
Can you run that by me one more time?
Oh yeah, I have a simulation here.
You're getting there, okay.
Oh yeah. So here's a little simulation I wrote that shows a swing. Imagine you have a kid swing and you're putting, it's all online, okay, you can all have it. You don't have to push very hard, you just have to push consistently with the same frequency and the swing will go higher and higher and higher until your child flies off or something. And if you match that frequency, this works really well. And this is again shown on the left side. Now, in a second or so, now here I'm showing it when I use a very low frequency. You can do this for hours, nothing's gonna happen. It's not gonna work. You need to have, the frequency has to match, right? At least somewhat. You can't just, if the frequency is too low, nothing is gonna happen. Here I'm doing it again, but now there's just some mismatch of the frequency. It still works, just it doesn't work as well. Of course, we could say in an electron, there's many different energy levels. So you can imagine you have many swings. And when you have a certain, when you push with a certain frequency, it will swing those swings that actually match the best, and the others will be touched just a little bit, right? Yeah. And again, this is interactive. You can run, change the sliders and all that. I won't have time because I have a lot of slides. Okay. So another thing I wanted to show you, these transitions are not instant, right? Here's a rope. It has a very, the smallest energy level. And now we are introducing another frequency on top of it. And you can see it starts to swing more and more. And now we are reaching the next energy level. And as I am increasing, the perturbation, it's now reaching the next energy level, N3, and so on. And you can see this is a continuous process. There's no magic. It's not instant. It takes some time to do that. And there is actually, so I think this quantum, collapse, it's actually something that takes time, and hopefully we can study it. I don't think this is anything instant, Yes.
So just to make sure I'm getting it, the idea is that Fermi's golden rule gives the probability of a transition given a particular perturbation.
Yes.
And the probability of transition goes way up if the perturbation is at the critical frequency of that system, which is just like resonance.
Yeah, exactly. So now here comes Sergey Rashkovskiy. He has written many really good papers, and I really encourage you to read them because I don't have time to go into the details. He has written one where he explains this. So he explains how you can explain the effects of the photoelectric effect using a classical light wave. The thing that's quantized is the electron level. The atom is quantized, not light. The light wave is continuous, and the resonance is basically helping to lift the electron to the next level using Fermi's golden rule. So hopefully this makes a little bit more sense now. And even further, you can calculate the time it takes based on the intensity. This is a chart on the right side here. So as you increase the intensity, the time will be reduced. And our clocks are now so good that we can actually measure that. And there have been some experiments where they measured the time it takes for the photoelectric effect in the attosecond range. But what he's proposing is that let's do another experiment where we actually try this. We use different intensities, and we could see whether that's actually the case, where when you have lower intensity, that it will take longer. That's an experiment we could do. Again, sorry, I won't have time to go all the way into detail. And of course, he has another paper on the double slit experiment, and it's really the same thing. Basically, we can interpret these experiments with classical light waves that are continuous, and the quantization happens at a detector, because the detector is usually electrons in some way or another that you lift to the next level, and that event is quantized. That's the only thing. And everything else is really, really simple. When you once you have that, you can calculate. This is basically a simulation from his paper that I implemented his math, and it works out well. There's another experiment I won't have time to go into, but I also have a simulation. That's the Wiener experiment. If there's time at the end, maybe I'll talk about this. It's even simpler than a double slit experiment. And if you click on the links, you have the formulas and everything there. So now this is speculation on my side, okay? I'm just wondering, what is a single emission event that we call a photon? I would guess, based on Fermi's golden rule on that, it's probably some kind of pulse. It looks kind of similar to what Donald had. It just, I have like half of it. So I imagine something like this when you emit it, it will keep pulsating for some time, right? It's not going to just be like one sine wave and that's it. I assume it will be some kind of pulsating wave. And here, viewed from the top, of course, depending on how it's emitted, I would imagine this is some kind of circular wave pulse, like in a radio. When you have a radio wave, it will go onto all sides. It won't just be like a single packet that's localized in all the dimensions. I assume it would spread just like a water wave would in very similar ways. So let's go to the Stern-Gerlach experiment. So this was an experiment where they flew silver atoms through an inhomogeneous magnetic field. And back then, initially, they thought, there's a spin, it has some direction, and when you fly through the magnetic field, it's going to land up, somewhere along the detector screen based on how it's oriented. It's going to be pulled up or down. And they were expecting this to be sort of a continuous pattern, the classical prediction. But then what they saw was the pattern was split into two parts. And the conclusions that they have drawn back then is that, the spin doesn't really exist until it's measured, that this measurement somehow collapses the spin right there. Now, again, we have to look at this in the historical context. So back then, this was actually before Pauli proposes the model for spin, before Dirac. And they didn't know a lot of things back then, again, right? So, for instance, they didn't know about nonlinear dynamics. They didn't have simulations methods that we have now with software. They had a really hard time with that. So if we revisit this experiment now with the knowledge we have now, maybe there's a different way to interpret this result. And again, Sergey Rashkovskiy, I encourage you to read his paper. He has written a very good paper about this, where he explains in detail with mathematics and everything how this works. I've written a simulation again, and I won't show it now because I don't have time, but if you go to the simulation, you can see the formulas and everything. Basically, the idea is that the spin exists before measurement, but then as it's flying through the magnetic field, it reorients itself. Well, actually, it precesses, and then it orients itself towards either up or down, and that depends on the angle, and it depends on the strength of the magnetic field. And which obviously then, separates the spins into two different attractors. Yes?
Does he have any way of dealing with spin 3/2 or anything like that?
I don't think he has done any work on spin, just 1/2, just spin 1/2, yeah.
Is there any possibility, is there any reason to think it could deal with such spins, spin 1, spin 3/2, etc.?
Well, I assume if the property of spin would exist for spin 1/2, it would also exist up front. I don't think there's any, but this experiment shows the way he's interpreting it, there's no magical collapse in that sense, so this property has actually existed before. right? It was just interpreted in a different way. So basically, he's saying the spin are initially uniformly distributed, and then they evolve over time. And there's this critical angle that determines whether the spin will flip up or down, and there are clear mathematical formulas involved, and you can calculate these things. And again, this is a screenshot from my simulation where we can reproduce actually the image you get on the detector screen. And what's interesting about this is that based on the calculations, if the magnetic field is not very strong, you should get no splitting. So, and that's something, again, we can verify in an experiment, right? So far, the conclusions, and of course, there are many more such experiments, but all of them can be explained with the classical wave, where the quantization is really because of the way we detect or emit. Usually photons are emitted from electron level jumps or detected that way. That's where the quantization comes in. So it seems like we don't need particles necessarily. And, spin seems to exist independent of the measurement. So let's get back to the medium. So what James have proven yesterday that there must be a medium if we accept that things are locally affected. Yeah, I did it last night. And, he has shown that there must be some kind of medium for matter waves, electromagnetic waves, and for gravity, and they are connected somehow. So let's investigate that further, how such a medium could work. Now, of course, the challenge is really, you can't just look at general relativity. You have to look at all of the things. It's got to work out for charge, magnetism, and everything. And that's what makes it really hard, right? So to be open-minded, of course, we have to always be open-minded since we don't know the truth, okay? So we have to look at what kind of medium could it be. And I'm just highlighting 2 rows here because otherwise it will take up the whole time. We can look at no medium, and I think we all agree there must be medium, because also no medium doesn't explain anything at all. Yes. Of course, there's some people who think it could be super solid. Some people think it could be like a liquid crystal. There's the elastic solid, and they all have pros and cons. I just want to point out 2 properties that we know of. For instance, that's the electromagnetic wave. From that, we can, I think, infer that, because basically based on what you said, James, that it's got to be an elastic, because otherwise you couldn't explain how in one part of the wave pulls up the other parts of the wave. It's got to be elastic, right? And it's got to support shear waves, so transverse waves. So it's got to be pretty resistant to. It can't just be a fluid, otherwise you would just. The wave would be.
Saying the nature of the second position derivative being related to the second time derivative at each location is the mark of elasticity.
Yeah, exactly. Yeah. So this, I think, would rule out a lot of the possible properties of this medium. Another one which I like to talk about is spin 1/2, because spin 1/2 has really weird properties, like the repeat of 720 degrees. And you can't do this, if you have no medium at all. If you rotate it, well, that's 360 degrees. You're not going to get the 720 degrees. You can, no matter how hard you try, right? It doesn't work. And for this to work in a liquid, it wouldn't work either. So the one I know for sure it works for elastic solid. It may work for like a biaxial liquid crystal, but so that's something we should explore, I think. But I'm focusing now on the elastic solid because that's the one I have looked at the most. Now, of course, what do I mean with medium? And of course, I don't mean something made of atoms, right? It's something, it's obviously not a material we know of. And it's hard to describe using words because we always misinterpret. So whether we call it ether or just vacuum. And, the funny thing is that the mainstream science uses the fabric of space-time. So they use words like this too, right? And even when you think about the Big Bang, although that's a totally different topic, they're saying that the space expansion stretches light. So even they say there's got to be something there, right? And I don't know what that something is, but we can describe the properties of this medium, whatever, or vacuum, right? So we know, for instance, it has to support shear waves. But of course, in the simulation, right, I will use grid points and stuff like that. That doesn't mean these points are actually there. Now, interesting is, from a historical perspective, there are actually quite a few researchers who have actually visited this idea, including Kelvin. He has thought the universe could be an elastic solid. Obviously, Maxwell had this mechanical model, right? He viewed the electric field as displacement of something. And he actually suggested that, it really helps, even if you can't find out the details, it helps as a mental model to understand how these things work when you have a model like this. And then we'll talk more about Newton. And of course, Einstein himself said, right, that space needs to have physical qualities. Otherwise, space without, and it wouldn't really make sense, right? So I think it's not too absurd to look into this question, basically. So, of course, I don't have that much time. I'll only touch on this subject for a very short time. And I think special relativity is the easiest one, so I'll start with that one. So when we have a medium or something that has the properties of an elastic solid, what we can say is that the speed of light should be constant for a particular density and so on. So assuming we have a homogeneous medium, then the shear wave can be calculated as the square root of the shear modulus. This is the resistance to twist, divided by the density. So if you assume the density is constant, then the speed of the wave is constant. Oh yeah, it's another simulation. It's just showing some examples of waves, transverse, longitudinal and so on. And again, this brings just some visualization tools to help you actually see that. So now imagine we had a clock in this medium, and my clock is just a wave going in circles, okay? So I call this, when the red dot is around one circle, I call this one tick. And of course, we are outside of this simulation. We can, measure, I'm counting like 4 seconds, let's say, for this clock. This is one tick. So what happens when we move that clock? So here I'm moving it. You can see the stationary clock is still there, and then there's the moving clock. Well, what happens is that the wave speed is the same, right? But now it has to travel a longer distance. So in the moving clock, the black circle there, the whole wave has to travel for this. And so of course it takes longer because the speed of light is constant, in the medium. So what you might object is, whoa, wait a minute, this doesn't that mean there's like a preferred frame? And oh my God, that can be drama. So actually, yeah.
It's okay.
No, the thing is, you can never detect it, unfortunately. It seems like a conspiracy, but actually, and I had the crazy idea that I can show we can find it, but we cannot, Anyway, here's another simulation that is online, inspired by Robert Close. Oh, Robert Close has written a lot about this, so he has a book and everything, so you should definitely read his work. This is maybe easier to understand also. Imagine a sonar, like a sub in the water, and you have a sonar clock, and when it's stationary, it's just one ping is like the sonar going up and down. That's what we call one tick of the clock. And of course, when you have the moving sub, right, it's the same thing. It has to travel a longer distance. You can see that with a dotted line. So in the speed of the sound wave, in this case, is again constant. So it has to travel a longer path. That means that clock is ticking more slowly. And I think this is really, really simple. And the thing is, just briefly, because the details take time to explain, but you can imagine we were measuring the speed of light now. We are smart. Oh, we want to detect the preferred frame now, right? We are smart. So we are doing this experiment where we measure the speed of light, and we get this is in pixels per second here. The thing is that even though, for the moving sub, the clock ticks more slowly, we also have space contraction, and now it just cancels out. You get the same result. Unfortunately. So no matter what you do, you actually get the same. This is a rounding error. So the thing is you can never detect it. This is really bad, really unfortunate. And I tried, and the people, James Blackmon, he was supposed to be here. He actually proposed an experiment, and I simulated it, and then we figured out actually it's not working because you cannot detect it. This is too bad. And Robert Close has more simulations and papers on this with all the math, so I'll let you read this on your own. So let's talk briefly, about general relativity. I don't have 2 hours on this. So what does that mean when we have an elastic solid? And interesting, Newton had some good thoughts on that, which I just recently found out. I don't know if James or someone sent me the link to that, but basically he thought that maybe, doth not refraction of light proceed from the different density of this ethereal medium? And he thought actually there was that, this medium had some elastic force. and that this could be the cause of gravity. So he even imagined that, imagine like these shells of like glass or something with different refractive index that would bend light towards the wherever matter is. And I think it's pretty amazing. And I'm really amazed when I saw this. I'm like, wow. And, at that time that he had this idea, that's pretty amazing. So, well, maybe this isn't such a crazy idea then, because actually in laboratories, they use this general relativity in the laboratory, for instance, for optical black holes, or there are also acoustic black holes. And this is a real image from an experiment where they have this metamaterial. So it's like imagine like a glass, but it has different, it has a gradient of refraction, right? So basically you have increasing refractive index, and when you shine laser light on it or whatever, it will start to curve more, and it can, basically imitate, it looks like a black hole. On the right side, you have the calculation, and the left side, you have the experiment. And this is the optical analogy of general relativity. And there are other experiments like this, which all use optics, but it's basically based on general relativity. It's the same mathematical formalism. You can even do this in your kitchen. You can have a bowl of water, and you put sugar in it. Just make sure you don't stir, so you have a gradient of sugar. And so that yeah, right, creates a refractive index gradient. And then when you shine a laser light through it, you will see how it bends. And that, I think, is pretty cool. Interestingly, so what is refraction actually? And it means refraction actually, it slows the speed of light. So when you have a medium with higher refractive index, you have a slower wave speed. And I think, Alexander has talked about this too. So this is a very simple explanation, and it's well studied. We know that a medium with increased optical index has a slower speed of light. That would also immediately explain why clocks slow down in a gravitational field. And Hagen Kleinert has worked out all the math. He has proven that mathematically it's equivalent to the Minkowski spacetime. So we can have this three spatial, and sometimes I just say density, but actually it's optical density. I don't know if it's actual density of the medium. By optical density, I mean increased refractive index, right? But sometimes we use sloppy words. So yes.
Now when you say density, that's an analogy. But when you say that it slows the speed of light at that location, that's not an analogy, right?
That's not an analogy,
Yeah, that's part of your...
Yeah, absolutely. Yes. Yeah. And this is called the optical mechanical analogy. And if you Google this, there are many papers on this. So people have been using general relativity in optics for quite some time. And this also, of course, implies that matter and light are waves. And this is a screenshot from one of your videos, Chris. And I'm not going to say more about this. Your visuals are great. So if you want to understand the metric tensor, go look these videos. Basically, what it does, right? It maps one coordinate system to another one. And I just wanted to point out the G00 here, which refers to the time. So basically, what I have done here, right? I have done a simulation using an optical medium with this a gradient of the refractive index. And here's the calculation. You can also click on the info. You see the calculations. It shows you the speed of the light at that point, the refractive index. And basically, in this case, the G00 would encode how much the vibrational frequency has slowed down. So, which basically means it's not time that's slower. It's really clocks run more slowly. So that's a big difference. It's not time as an abstract concept. It's, So, and how does it work? Like basically the idea is that regions with high strain, so where already there is mass. What is mass? When we talk about mass, we mean waves, right? Matter waves. The matter waves introduce strain into the medium. And we have seen from the formula before that the speed of the light depends on the strain and the density. So when you have added strain, it basically slows down the speed of light because the added strain. So this is a quick explanation, and Robert Close has written a whole paper on this to explain this better. So, I want to talk about that. Basically, the energy. What does that mean, mass? And so one way to interpret interpret this is that when we look at the wave, this is just some wave, it's just some random wave, and I'm showing two planes here. But when we look at what kind of energies do we see in here, there's different kinds of, there's a potential energy, and there's also kinetic energy. And the kinetic energy is just how fast, like this one grid point that I marked is moving at the moment in this oscillation. That's the kinetic part, and the U is the displacement. Then we also can imagine we have compression, which is energy, and then a twist energy. So the overall, if you have a particle, in quotes, in a certain volume of space, when you integrate over this whole volume and you add up all the different kinetic energy and the strain and the compression, you get the overall the energy in that volume, and that corresponds to what we call mass, basically. So this is basically all it is. So there's no concept of really mass, it's just basically energy. Yeah, okay, I do have a slide on that. Yeah, so basically, how do more waves slow down light? I think Alexander asked this in a recent YouTube video also. And so basically, we can use the optical analogy. And we know that the speed of light depends on the modulus and the mass density. And so when we add extra mass, meaning we add extra wave energy, this wave packets add basically mass density, and this is a concept from linear elasticity. It is well known that there are papers and books about this, so this is nothing really that magical or anything. And simply by doing that, basically you just add that additional mass density, you calculate the new speed of light. So it's actually not very complicated. And again, Robert Close has written a paper on this. Yeah?
Is that only where the mass energy density is located, or does it spread out?
That's a good question. Of course, a wave is not like, it doesn't stop here, right? It's not like there's a wave and boom, it stops. So a wave is spread out, right? So.
Can you account for gravitation?
Yeah, I do. Oh, yeah, there it is. So if you have, basically imagine this is Earth, and here is a plot of zero from the center of the Earth out to the surface of the Earth, and then you go farther away. On the left side, it looks exactly like the gravitational potential, but I'm actually using the refractive index, and I invert the coordinates so it goes downhill. So you get. So basically, this is more. In here, you have a higher refractive index than here, and the derivative of this is the acceleration, right? This is what sometimes people confuse, I think. So you can see that at the surface of the Earth, you have the highest acceleration, because it's just a derivative. At the center of the Earth, there's no acceleration here, and also again far away. So the acceleration, of course, can have sharp turns, but the overall so this is the derivative of the refractive index, basically. It's fully consistent with general relativity, as far as I can see. So I will skip this one because I don't want, I have to watch my time. So
you have an hour till the Q&A.
Yeah, I have a lot of slides. So let's move on to electromagnetic waves. I hope you have some coffee ready. Let's take a look at that now. So if you look at Maxwell, we have to figure out how do we define what he has, what's the magnetic field, what's the electric field, and so on. So here, what we can do is first of all, we look only at the transverse part. Using Helmholtz decomposition, we can just use it as a transverse part. And we can define the electromagnetic vector potential as the derivative of the displacement, which basically would be like velocity. So here you have more velocity than, say, out here. Interesting is that Kelvin actually had the similar concept. So he was also thinking about velocity of this, he calls them particle of the medium. And Maxwell had this mechanical model where he thought something was actually rotating, right? Which I thought was very interesting. So maybe something is rotating. So when we look at this more closely, when we have B as the curl of A, and if A is a velocity, then basically the B is really when you see here's an image or a simulation of the B field is pointing upward here, because this is basically imagine like a wobble motion in this elastic solid, like a pudding. You can imagine this. So you have the velocity, and then you have B is the curl of A, which is pretty simple, I think. And it will also correspond to angular momentum density. And then the electric field. So again, A is the velocity field. So we have the derivative over time. And for the electric field, we have two parts, right? We have the displacement and we have acceleration. And of course, the details depend on what charge is. And now, if I have time, I will talk more about charge. But its principle is actually quite simple. And when you put this together, this is inspired by 3 blue, 1 brown. I wrote a similar simulation because I just like to play with this. It just looks like fun. If you want to play with this, you have different sliders. You can try different kind of waves. So this is what basically an electromagnetic wave might look like, approximately. In one slice, of course, in the medium. This is not in 3D. This is just in 2D. So now, of course, remember before we have seen that when you have like this wobble motion, you get a magnetic field. But that's actually not yet spin 1/2, because spin 1/2 requires the 720 degree. And also, in spin 1/2, we actually want to rotate something, right? Somehow we want a rotation. We want to have an angular momentum. And I think it's important because a lot of people just discard it and they don't even look at spin 1/2. I think it's important because that's what made me first critical of this idea of the elastic solid. I'm like, we have to explain spin 1/2. If you can't do it, that's not going to work, right? And it has a lot of interesting properties, right? The angular momentum, the 720 degree. So I encourage you to try this experiment if you haven't tried this before. Imagine you're the elastic solid. You're glued to the floor, and you have this particle here in the middle, and you want to rotate this now, okay? And you can't let go, okay? You can't flip it either. It's gotta, and you do want something that goes like this, and it repeats after 720 degrees. Yeah, try it. I know James can do it. So think about this. How can you rotate? Yeah, I think Alexander.
1.
Yeah, you can do it exactly.
2.
Yeah. So you can also see I'm starting here, right? I'm rotating it. Now it's 1 times around 360 degrees, but my configuration is not the same. So I'm going around the second time. Now I'm back to where I started. So it takes 2 turns. So when you do this a few times, you can see it takes 2 turns, 1 turn, 2 turns, right? 1 turn, 2 turns. And you can actually connect this if you want to somewhere. It still works, okay? That means it's actually a valid rotation in an elastic solid. You don't break the elastic solid. It's all connected. And the thing is, you can't do it if you don't have a medium. You can't do it. It will repeat after 360 degrees. So that's actually, to me, a strong argument to say it's got to be some kind of elastic solid. And you get angular momentum, right? Even though, if you look at it closely, the spinor, it's not really a rotation. It's like a winding and unwinding. But you get the angular momentum, even though it's an elastic solid, which I find pretty amazing. But if you imagine this was like a really heavy bowling ball and you do this, right, you can see that there's angular momentum. It's kind of hard to visualize, so I have way too many simulations on this. I will only share a few. You can all have this and play with this. This is the typical Dirac belt trick animation that you see in some other YouTube videos that shows you how you can connect like a belt. You can connect something to the center, and it doesn't tangle up, basically. I've also highlighted some points in the medium, in quotes. You can see what kind of shapes it's tracing. So it's tracing a circle. I won't spend too much time on this. Robert Close also has written on this paper, and so I've implemented, of course, I've written a simulation on this. Here you have the spinor in the middle. It's the same thing, but he added the Bessel function. I think Donald also has a Bessel function. This is a Bessel function on top of that. This is just 2D. So, of course, we have to imagine this is actually in 3D. Of course, there's another simulation in 3 dimensions, and if you launch the simulation, you can slice it, and you can, do all kinds of things. So here's what it looks like a hula hoop. I think, James, you coined that term. It looks like a hula hoop dancer. From far away, it looks like a hula hoop, and then when you slice it inside, you can see that rotating motion, and also the B field here is pointing upwards. This is combined with the Bessel function. And again, a slice, and of course, in 3D, it's a little hard to see, but if you slice it and dice it in different ways. So basically, it's a pure wave. It's basically a transverse wave, and spinors are really fundamental waves of 3D space. Oh yeah, so here I just for fun I added two spinners side by side. I flipped them around. So here I have like the North Pole against South Pole, and you can see how the magnetic field aligns. So you would get an attraction. And I didn't cheat. So basically I really calculated each spinner separately, and I just added the waves up, the wave amplitudes, and you get automatically, you get this right away. And then here's the opposite. I basically, it's a south against south, and you can see this will result in a repulsion.
You finally figured out how magnets work.
Exactly. I'm just doing this for me, okay? I just want to understand how these things work, and I'm okay now. I have like this picture, you know, where I can imagine how this would work. What's between the magnets, right? So maybe this is also has something to do with the Zitterbewegung, right, that we hear about a lot, because these massive particles, they all have spin 1/2, and so somewhere in the core of these particles there must be this spin 1/2 wave, which is something that's going around in circles at the speed of light, obviously, because it's a wave. So maybe this is linked to the Zitterbewegung. I don't know for sure, but you know, it seems like a reasonable candidate. You can also see that each point, I mark different points in this medium, like Smarties in the pudding. You can see there's little circular motions everywhere. So it's actually a spin field. It's not just at the center. You have a whole spin field. Sorry, my... So what could an electron be? And of course, I don't have the full answer, but I think it's definitely something that's a localized mechanical standing wave of some form. It definitely has, I think, the spinor wave mode inside. That's just one part of this. It also has, of course, the orbitals, the standing waves, which are defined by the spherical harmonics. And here is elaborate simulation. This link here is a very complicated simulation. It has a lot of, you can put in all the quantum numbers. You can get, you can simulate all the shapes from all the orbitals. These are just different examples of different quantum numbers, what it might look like. So this is basically the spherical harmonics. I also have a simulation with the vector harmonics. So this one is the magnetic vector harmonics. And then there's also a mode where you can, and again, this is just different wave modes. And I have a slice, I'm slicing through it because if in 3D, it's kind of hard to see, but you can slice it in different ways and thickness. And the arrows are the magnetic lines. And then in a moment, you will also see an example of the electric vector harmonics. So here's the electron.
Do all of these evidence the spin 1/2 quality in what we see right now?
This is based on the spherical harmonics. The spin 1/2 would be on top of that, right? The spin 1/2 wave is basically on top of that. Yeah. Yeah. Okay, so how much time do I have?
You have about 20 minutes remaining.
Oh, wow, I think I was faster than I thought. That's good, though, I have some time. Now, okay, this is not going into speculation because what's bothering me right now is what is charge? And I haven't seen a good answer yet. I know Donald has talked a little bit about it, but I want to know more. Like, what is a single electron, when you have a single electron that's charged, what does it look like? Like the wave, how does it stay stable, right? So I've been trying to explore all different kinds of models because I don't want to just limit myself to one model. We have to make sure we find the true model, so we have to explore different ideas. And the thing is, it's like a puzzle, like the spinor thing, it's like a puzzle. So we know, for instance, that there are two types of charge. We have the Gauss and the Coulomb law. We have time reversals. That means if I run a simulation backwards, it would result in the same charge. If we create a mirror image, we have also the same charge. A charge can move freely. Then we have charge conservation. And we think the net charge in the universe is approximately 0. We don't know for sure, but it seems to be close to 0 at least. So this is like a bachelorette party of the charge contenders. Different, how, what could charge be? And please let me know. I want to know from all of you later on, like, what do you think charge is? Because I haven't really, concluded yet at all. I think right now we can rule out certain models, but I'm not sure we actually know for certain. I'll go through each one of them. So the easiest one is longitudinal standing waves. Then we have these transverse radial oscillating waves. We have several researchers have a model of sort of toroidal shapes and oscillations. Then we have the micro-rotations, director fields, and inclusion-exclusion, and I'll talk about each one of them. The easiest one to understand is charge as spherical waves. So that there are two types. There's standing and there's traveling. So here's an example of two charges, in quote, two centers, and this is a standing wave. So we have you can see the standing wave pattern. This is something Jeff Yee has worked on, and he has a really nice model. And this is a traveling wave. Yes, go ahead.
By charge, do you mean like a property of the matter or the generators of the Coulomb field?
Like an electron, like what's the charge part? Like we understand the spinor.
In particular, in terms of the thing that's generating the Coulomb field.
Yeah, exactly. The thing that, yeah.
Because then there's also charge as part of current.
Yeah, of course. So I mean mostly the static part, the static charge, because that's the one that's puzzling. The other one I can understand, but yeah, because the static charge is puzzling to me. Like, so the spherical waves would work in principle. So mathematically it works out if you use the standing wave. The traveling wave won't work because a traveling wave transports energy away, so that can't work. So now there are pros and cons to this. The pro is, again, there's more simulations on this. It's simple, it's trivial, it's spherically symmetrical like it should be. There's no angular momentum, which is correct and all that. But the thing is, if you think if it's a standing wave like this, then what is the plus and minus charge? That means there would be, plus and minus would be differentiated by a phase shift. That means you need, like, throughout the universe, you would have to have this phase is plus charge and this phase is minus charge, which seems a bit tricky. I mean, it doesn't mean it's wrong. Also, there's no charge conservation built in. Like, why can't you just generate a standing wave that's plus charge and no minus? So that's a bit fishy, I think. And also, I don't think it conserves the phase when you move it. I think the phase will change. So suddenly then a plus charge can turn into a minus charge. So unfortunately, I don't think that model works out. I wish it would. If you can show me I'm wrong, I'm happy to discuss it, but I don't think this works out. So then, of course, I had my own little pet idea, which I think is actually also wrong. But anyway, I thought, hey, I know the answer. I thought, it could be these transverse little oscillating waves. And then you have plus charges one way and minus charges the other way. And you can make it so that it's spherically symmetrical. And when you look out from the center, it's always the same direction. And the math works out, okay? You get the Coulomb law, everything's fine. Here's some examples of plus and minus here too. This is again plus, minus, and I think it zooms in. So you can see like there's a little tiny wobble motion. The math works out fine. It's simple. It's really simple in a way. The problem is, and again, this is a slice, a 2D slice in a 3D elastic solid. It works out mathematically, but, the problem, and it's transverse. The problem is, sorry about that. When you reverse the simulation in time, you flip charge. And if the time reversal thing is correct, then that rules it out, because if you reverse it, it's no longer moving the right way, it's moving the left way. So that means that's probably not it, unfortunately. So now there are several researchers who have similar models like this. There's different kinds of oscillations that are on the surface of a toroidal shape, for instance, and you can, there's different mathematical ways you can describe that oscillation motion. This is another way, and then and I won't even name the researchers. It's just from different. I know different people have this model. So is that a possibility? So maybe then the direction again. And you can already see the problem, right? If the direction is charged and when you reverse time, that's going to flip it. So that probably won't work. Oh, sorry about that. So the problem here is that when you reverse time, you reverse the charge. So that can't be it. Plus it has angular momentum. Yeah?
Why would that be an issue, the time reversal?
Well, I don't know if it's proven or not, but I thought it was proven that based on the standard model, right? The time when you reverse time, you get the same charge, unless that's wrong, and then I would be happy.
Like, what does it even mean?
Yeah, I'm not sure. So let's talk about this, because maybe if you're right, I will be very happy. Yeah, go ahead.
Yeah, I mean, you have to reverse charge when you reverse time. I mean, that's why I think Joliot-Curie missed the discovery of the positron, because they were in error about the direction of the particle. They think that it was going into the nucleus, it came out of the nucleus. They were in error about the direction of time.
Oh, well, let's talk about it then. Maybe my model is correct after all then. I'm not just kidding. Okay, that's great. That's when I want to present this, so we can talk about this. So, but the problem is here also there's angular momentum, and charge shouldn't really have an angular momentum as far as I know. But maybe there's a solution that it's not really spherically symmetrical either, so that's another challenge I see. Maybe, we should talk about this if you think that's a possible model. There's also, now another thing is this Koserat micro rotations. Now, imagine when you have an elastic solid, each little, let's say there's a Planck particle, or whatever you want to call this, in the granular structure. If this granular thing also has like a little twist to it, like a micro rotation, you can imagine the neighboring having a little more twist, and the next one having a little more twist, and the next one having a little more twist. This is called I don't know how to pronounce it, Koserat micro rotations, and you do get charge that you can easily model charge that way by basically, using these micro rotations. That seems like a valid model. I haven't really spent that much time on this, and it looks nice. And you play with this, but and again here it's basically a topological property. The thing is, what I don't like so much about it, it makes the medium more complicated. So do we really have to introduce this additional concept of micro-rotation? Maybe we do. And how exactly do we couple it with electromagnetic waves, right? There has to be a simple reason how to do this. But there are papers about this. So this is something we might need to explore further. And I think this is similar. I'm not sure if Donald, if this is your model or not. I'm not certain, but I was trying to think about what you mean with the dielectric medium, and I was trying to figure out what could that mean in terms of charge? And I could see that we could turn this, we can have like this director field. So when we, have like this, imagine like little dumbbells where one side is plus, one side is minus, and we flip them. So when they all go, like the blue side is out, they have plus charge. And when we flip them, you have minus charge. And it works out really nice. So, but I don't know, I would like to ask you after, like how do you imagine a static charge? What does it look like, in the medium? There's another one. Now, of course, if the time reversal is correct, Alexander, and this one will be wrong, but this one is a really nice, simple one I just recently thought of. Actually, thanks to you, James, because he told me about, I think, Maxwell's book, and then I read Kelvin, and he had this thing, and you talked about pressure, right? You kept mentioning that in the YouTube video of this pressure, and like, maybe there's really a simple way to do this, and actually there is. It's like you can visualize charge as an inclusion and exclusion. And I don't mean like an extra thing stuck in there, but basically, I don't know if you can see it in the simulation. It's maybe a little bit hard to see, but basically we just push like one little grid point a little bit over, and that will create a place where there seems to be one missing, and on the other side you have one extra. And that's obviously you get charge conservation there for free, right? Because you can never just create a plus charge. It's always two at a time. It's always plus and minus. It's stable. It's their time reversal would not flip it. So if time reversal does flip it, then it wouldn't work. This is really, really simple, actually. And I have read some paper. Well, I haven't read the full paper, but I Googled it, and it's basically volumetric eigenstrain, and it is stable, which is interesting. So to me, that's like a valid contender. And how does it move, though? See, the thing that bothered me first, I thought, well, if you have this defect, how can a defect move through the ether, right? There would be some resistance. So the thing is, it moves more like the Newton's cradle. Imagine when you have this Newton's cradle here, right? The red ball doesn't move through all the other ones. It just pushes on the next, and the next one pushes. So this is similarly, like in this case, the inclusion or exclusion would just, like the purple one here would move towards the yellow one, and the yellow would push further. And overall, the order stays the same. It's just like Newton's cradle. So that way, charge could move freely through the medium like this. Yeah, I mean, I kind of like it just because it's so simple.
I think that is charge in a wire.
Maybe. See, I don't know. Yeah.
Current in a wire.
It's possible. Yeah, it's possible. Yeah, it's you know, you get Coulomb law exactly. It mathematically works out. So we have all these contenders, and I think, of course, I'm not sure. Maybe you can prove me wrong. Maybe I was wrong about the time reversal. But it seems like the standing wave is probably the most tricky one. I don't think it can work out because of the phase. When you move it in special relativity, when you move it, you lose the phase coherence. So I don't think that will work out. The lower three, I think, are contenders, and these two, I think, if time reversal is correct, then they will fall out. Maybe there are other ideas, so I'm hoping to hear from you guys if you have any thought, any brainstorming. What is charge? As a summary, I think the universe as an elastic solid I think we can derive a lot of observations like special relativity and quantum mechanics from this single medium, like Donald was saying. We don't need 200 fields, we just need one field that it can explain all these concepts. And at least it's a nice mental picture that helps us understand, at least for me, it helped me a lot to understand how all these things work together. And I'm hoping that we can, you know, interest people to work in this area and do more research to find out more. And of course, thank you very much for a lot of people. So this material is based on a lot of authors. This is not just my stuff. My contribution is mainly the simulations. Also, I've had lots of discussions with lots of people who each time there's a debate, you know, there's another idea that flows in, which is great. Thank you very much for your attention. And yes.
Experimental results give us another idea about the emission of a photon. It does seem to be directional because the electron will even recoil in the opposite direction of this emission. So you get a kind of conservation of momentum. And that directional, once it's emitted, I think it begins to spread as a wave.
Yeah, maybe part of it's absorbed, right? Maybe the wave goes in both ways, but because of the atom is there, it will absorb it again, right?
Could be. Yep.
So it is emitted on both sides, but then it's just absorbed.
And that helps to explain some of the time delay questions, because it seems like it immediately happens at the speed of light, that it will affect the detector, even though it's a single photon emission. But if it is directional, in a sense, and if it's very high frequency, it doesn't diffract much.
Yeah,
and
maybe.
So you get all that energy, kind of going in one direction to the detector, and it makes them think a particle is flying through.
Yeah, right. Yes.
Now you mentioned phonons as sort of an inspiration for all of this, but and from what I understand, you're saying a phonon is a mechanical oscillation.
Yeah.
And yet it acts like a particle. So I have two questions. Number one, isn't a phonon, this is sort of devil's advocate, isn't a phonon itself a quantum phenomena? Isn't that
it's a vibrational mode. It's described as a vibrational mode. So when you have
a quantum vibrational mode, so whatever funny is going on, whatever I shouldn't say funny, whatever additional things are going on in quantum phenomena that make it hard to account for them, it's going on in phonons, so you can't use phonons as an from the mechanism.
The reason is when you have like some crystal, like there's an end, right? So when you have vibrations, there's only certain vibrational modes that you can have in a crystal, because the end, like in a violin or cello, the ends are fixed. So that's you have these boundary conditions that limit the kind of waves that persist, right?
So phonons are classical in that sense?
Yeah, they're classical.
Oh, in what sense then do they act as a particle?
The detection.
Well, they can move. It's like they can appear. I don't know the details. Okay, I'll have to read papers. Yeah. But I know they're in the literature. You see them like called particles of heat and quasi-particles that appear to be moving, like how heat moves through, say, some metal, right? How heat moves, and that's described using these phonons. And it's funny that people call them quasi-particles and light. At the same, but yet, the phonons are clearly just vibrations, but it's described quantum mechanically the same way. So why should photons be so different? I mean, that was the one thing that kind of started raising questions. Yeah.
It is the detection mechanism.
Yeah, exactly.
That's what quantizes.
Yeah, exactly. Yes, absolutely. Yeah. Yes.
Hi, I'm delighted to see your simulation.
Yeah, beautiful.
And also, particularly, I think in the future, I hope that we can collaborate.
Yeah.
Maybe on simulation on the vacuum excitation as a dielectric medium.
Yeah, yes.
And particularly in the creation of these particle antiparticle pairs.
Oh, totally.
Because,
Oh, yeah.
Electron and positron. You know how you come from a electrically neutral medium, a vacuum medium, and then suddenly you're giving energy such as giving a gamma ray, and then you locally stimulate the separation of these positive and negative primordial charge, and now they become two.
Yeah, exactly.
That would be excellent.
Very cool. That would be very cool. Yeah.
Okay.
Yes.
I have some version I can give this you. Spinor, it's from global Spinor functional phase to the local process. Charges are topological tachyons.
What do you mean, can you explain what do you mean with topological tachyons?
Because there are two separated sectors in space-time, tachyonic sectors.
Okay.
And the phase go through those sectors in neutral linkage structures. And this my finding is so that each charge has their own interaction mechanism in this sector.
Okay.
It's spin half fiber.
I'll be happy to read if you have something like a link. I'm happy to read it. Yes.
Yeah, I think it touches one of the most fundamental questions regarding age. Is age, in the first place, the angular momentum of the atom, or is it the weird proportional factor in Einstein's E equals hf? So I think the more fundamental property is it's an angular momentum of the atom, and once that is changed by an incoming wave, then we have what you call the detection of photon or absorption. And I think, yeah, what you're saying points to the second alternative, that the angular momentum is the more fundamental property, and the other Einstein's formula is the derived.
Cool. Yeah, that's a good idea. Yeah, let's think about that more. Yeah. You?
You've given a suggestion on a physical interpretation of the magnetic potential and the scalar potential, so A and phi.
Yeah.
How does that change if we start trying to do that with Donald's idea of Z? Because it seems like Z is a alternative way of looking at everything to A and phi, right?
Yeah, I think the scalar potential would change. I would assume it would be like the separation between the two, how much separation there is. I don't know how to quantify exactly, but that would be the scalar.
I wonder if there are two different, another possibility is that they're just two valid ways of looking at the same thing.
Yeah, maybe. Yeah, we should definitely work on this and think about this more. Yeah. Yes?
In the beginning, you were discussing resonance in relation to like jumping through quantum orbitals. Were you suggesting that resonance is sort of related to wave collapse, and if so, can you elaborate on that?
Yeah, I do think so. I mean, because basically when you move an electron from one level to another, we can explain this with resonance, right? How an incoming waves increases the wave, and then, at some point it moves on to the next level, like with the rope you could see. And the reverse, the other way, and basically it can go in both directions, right? It can also go in the other way. So similarly, when a wave from a higher energy level moves down, it doesn't just jump, right? There's this oscillation, and if it loses energy, one part of the oscillation will go into what we call photon, right? And the other part, and then it will go down. It's probably pretty complicated, and I'm not. We have to probably work on more simulations of how this process works in detail. But I think it's definitely something we should study, right? How does this process work? Because it's definitely something that takes time. I don't think it's instant.
When an electron moves to a higher orbital, it seems like it actually takes on more waves.
Yeah.
Its wave number increases.
Yeah. Yeah, exactly. Yeah, it's like going from when you have a violin, you have this motion to when you have a node in the middle, right? Like, so basically the religious people who have this Ohm thing, they're probably maybe right, because the universe is just like this big orchestra of that's kind of funny, yeah. Yes?
Yeah, so about the what is charge question, so I'm not sure how much of this I can offer potential answer to, but because you still need a notion of charge to have the electrodynamic potential, so the vector potential, to generate vector potential, but I have a possible hypothetical explanation for how the Coulomb field would arise from that.
Okay.
Without postulating it at first, and this has to do with this, Zitterbewegung motion of these.
Okay, maybe you should have lunch and they can tell me all about it. Yeah.
So that's just another.
Okay. Yeah.
If you want to spend time on this, I would like to make the connection between the rotation of the mug in the hand and some of the simulations you've shown us. And I think that's definitely going to be helpful for me. I think it'll be helpful for a lot of people. Can you?
Oh, yeah. You want to go back?
Step by step. Yeah.
Do you want to go back to one of the simulations?
I've been trying to see it for months now.
Just you have to do it 1,000 times, and then you'll see it. Okay. Unfortunately, I'm not sure there's
a couple times, right?
I'm sure there's a shortcut. Yeah. Let's see. Where was it? Which one? I mean, let's see. Do I have internet access here? No, I don't. But let's see. I do have actually this. I have it locally also.
Maybe the single layer of hula dancing.
No, which one? Spin, solid. This is one of them.
Do you have all your animations like on a specific website, or?
Actually, I uploaded them all to your Google, your Drive. I zipped them up. Now I don't have internet. Unfortunately, I don't have internet, so I can just run the video now. I don't have internet here.
Wi-Fi password is written to the right.
I mean, I can also show you after. Yeah. I'm connected to. So I think the easiest. I can also show me the laptop afterwards, maybe when
This one looks promising. I feel like we could connect this animation to the mug.
Yeah, the mug would be in the center, right? The mug would be in the center. So let me just do this again. So this is from outside. This is basically, it's just literally this movement. This mug would be in the center. You can see it would be rotating. And like, this could be one of your arms here, like one of your arms.
What? see if you can.
Let's see, there's another one. I don't know, there's another one.
Keep doing the same thing over and over again. So my eyeball is.
This is not a slice. Yeah, this is.
Yeah.
But the mug would be in the center. It appears to go around.
Is it possible to do that with both hands?
Yeah, you can,
Okay.
Yeah, you can do it with both hands. Let's see how. So look, see, it's possible. Yeah.
One on top and one on the bottom.
Doesn't matter. Well, I don't know. My arms will do it. Yeah, you can. It's possible.
Oh, you have to.
Yeah, it's possible. Yeah, definitely.
From physics to sports.
Yeah.
So the little pattern. I really like this second one. My mind.
The second one. This one. This one.
Yeah, this one. My mind.
You can see the wave going around.
So the wave is the mug, and the relation of that wave with the rest of the medium is like the relationship between the mug and my hand.
Yeah, your arm. Like it would be one axis, one coordinate axis. You would go through. Like the x-axis could be your arm or something.
Could you keep repeating the same perspective? Just keep repeating this first part so we can keep.
Okay. Yeah. Sure.
So I'm keeping track of the divot. My eye wants to keep track of the divot, and so I'm following that divot around in a circle. That seems to be a 360 relationship, not a 720.
If you look at the standard, though, and then this visualization helps to see it.
Yeah.
Is the thing in the center rotates twice to get back to like this, just like what it did here, right? If look at the handle. Look at the handle of my arm, right? I'm starting here. One rotation. Like my arm is up here now. It's not the same. I didn't start like that. So now it's back to normal.
Is the ball here analogous to
the cup? It's just the center.
It's analogous to the cup, and is it analogous to the pattern in the blue.
Yeah, like the neighboring grid points. It's just show how the neighboring.
If we were to go back to the blue simulation, would we find a spot that
Yeah.
is akin
Yes, the
to
center.
the belts?
The very center, he would be like the sphere. That
So
part,
the center
that's
is doing 360.
it's actually doing 720, 720. Yeah, yeah.
The center is
Yeah.
also okay. I don't see it because it looks just like a mug doing.
I know, that's the funny
Center
thing.
looks
Yeah,
to
no,
me
no,
like
it's
a mug
this. It's you can see it, right? Because now the way the wave, the medium wraps around, it goes up and down. So like here's one, and then my elbow is up, and now my elbow is down again.
See, when you do it with a mug, I can see the mug's 360 rotation, and I can see the 720 rotation of the relationship between the arm and the mug. But when you show me these simulations of the medium itself, I can only it's as though I can only see the mug.
Oh
I
yeah.
can only see a 360. Is everyone else having the same problem, or can you see
your
720?
axial
Yeah,
Yeah,
I
exactly.
get it for the mug. I can see it with the mug. I can't see it in the
Yeah, so it helps. You have what I do is you can mark a spot on the sphere.
I can see it here too.
Yeah.
I can't see it in the actual wave simulation.
Oh well,
This
here.
is more like your actual vision of the ether,
Yeah, yeah.
right?
Well, it's the same. It's just the center one. The center is very small here. Like the very center point. Well, the center few
I think I just have to
pixels.
stare.
Yeah.
Raise your hand if you can see it.
This simulation, I think, is just a little bit too short to see.
Yeah.
Yeah, of course. It has to go. Yeah, longer. Right. Yeah, yeah,
You have only the first rotation. You can
yeah. Yeah, yeah.
I know you can see that.
Yeah, good. Yeah, yeah. And just use the links. I can email them or something. Can I? I have this basically.
At one point, you have to kind of see the entire. You can see the strain in the series of blue.
You can do a test and pose it.
I can send this page to everyone with all the links to the simulations. Yes, go ahead.
Excuse me.
Yeah.
Do you have any last pressing questions for Chantal?
Yes.
Concerned with aging, and we are near basic mechanics. So there are closed systems and open systems. And constant speed, there is a time dilation, but no aging difference. Then when energy change, there are acceleration and aging vary due to direction and intervals. Then the mass is like a retarded time with global phase due to like curves in space, and there are vibration of toroid helix and others in particles. I see this like that.
Okay. Yeah. If we can talk maybe lunch also. If you can draw me a picture or something, and then.
My paper.
Okay. Yeah. Okay. Last question now.
Yeah, I think Donald's model of a dielectric medium suggests exactly what I think the best theory is your directional idea of charge. And I always thought this from the very beginning, that somehow, there's this dielectric medium, and somehow all the positive, displacements get on the outside of this wave structure, and all the negative displacements or
I see what you mean. Yeah. Right.
get on the inside, and so you get an electron or a positron depending on which side is out.
Oh yeah, that kind of makes sense.
That's kind of your directional model.
Yeah, I think so. Yeah.
All right, let's give a hand for Chantal here.